Welcome everyone to the third lecture in this series. Last time we laid down the foundation, the mathematical foundation using white noise analysis to for us to discuss further more things about stochastic processes. In this lecture, we're going to calculate the probability density function, and we shall start with the simplest possible example. And the simplest example would be the Brownian motion, which we have seen last time, and we said that the Brownian motion could start here and end here, and then how do we calculate the probability density function? And this will be our prototype in the manner, the way in which we will calculate things. So we ask ourselves the question, how do we solve for the PDF or probability density function for this case? Well, we can start in this way. We can parameterize the fluctuating Brownian paths. So suppose this would be the position of the paths. It starts with the point x sub naught, and then so initial point x sub naught plus fluctuation given by the Brownian motion bt. And we have here a constant square root of 2d, where d, capital D, would be the diffusion coefficient identified later on. So given that type of parameterization, as we can see, the initial point x sub naught is fixed. But since the initial point is fixed, but since this is a Brownian motion, at the final time, capital T, the endpoint of this motion could be anywhere. It's random. So suppose we would like to, so we have a configuration or diagram which might look like this. We start with time t naught in our process. We end at some final time capital T. So the vertical line is the time, and this would be the position. So the way we parameterize the Brownian motion, we have an initial fixed initial point, but then it would just fluctuate as time progresses. It would just fluctuate left and right and so on and so forth. And it could end here, or it could end here, or it could end here. It could in fact end anywhere once we reach the final time capital T. Now suppose we don't want that to happen. Suppose we want the Brownian motion to end at a determined final state x sub t given by this position. So to do that, to pin down the endpoint at some chosen point in space, say x sub t, at some final time t equal to capital T, we can do that. We can pin down the endpoint by using this Dirac delta function or Donsker delta function, which means that this x sub function of capital T is of course given by this. So this expression, this x sub t can be written like this. And this simply means that we have an initial point, x sub naught, and then plus some fluctuation, and then because all of these are inside the Donsker delta function, this delta function is always zero. The way delta functions are defined, it's always zero. It's nothing. And when does it acquire a meaning? It acquires a meaning when the initial point plus fluctuation ends at some desired endpoint x sub t. So we have this object that means only those paths which satisfy this x naught plus Brownian motion ending at some x sub t, only those paths which satisfy that, then the delta function would just spike. It would just it would be non-zero only at that point. So writing this down explicitly, so we have this type of expression. Now this Brownian motion, as we learned last time, can be written in terms of white noise. This bt is given as an integral of the white noise dt. So now we ask the question, how do we sum all those paths which satisfy the Dirac delta function. So given this delta function, our figure, our diagram would look something like this. All the other paths are now gone because they have zero contribution to the story, and only those paths which start at x naught and end at some point x sub t would survive. So we would like to calculate in closed form the probability density function for this type of processes, and we can do that by adding all the paths which survive, which start at x naught and then xt, which are non-zero contributions to the delta function. So we ask ourselves the question, what is the expectation value of this delta function? And in fact, the probability density function, which we denote by this P, capital P, is the expectation value of the delta functions. So the probability density function, which is also the expectation value of the delta function, is an integral we sum over all Dirac delta functions over all non-zero contribution, of the paths, and summing is essentially integration. But since there's a white noise functional inside your delta function, the summation or the integration will have to make use of the Gaussian white noise variable. So that's the object for this lecture. We would like to calculate this object, integrate it, integral over the d mu, or the Gaussian white noise measure. Now remember that this x function of capital T is actually initial point plus fluctuation, or plus the integral of the white noise, which is simply the Brownian motion. So let's go ahead and calculate this object. So we have this object upstairs, initial point plus fluctuation, which should end at some final point x of t, otherwise the delta function is 0. And the first thing that we have to do, and you should remember this, is that you can always express any Dirac delta function in terms of its Fourier representation. So this means that whatever is inside the delta function, you can put this in the exponential e to the ikx, where x is whatever was inside in the delta function. So in this delta function, this whole thing would be our x in this Fourier representation, and it will be exponentiated. So using this expression, this delta function, it can be given by 1 over 2 pi integral of e to the ik of whatever was inside the delta function. That's this one. And then all we have to do is to sum over non-zero contributions. We have to integrate over this delta function, integrate over the Gaussian white noise measure. So expressing the delta function in terms of its Fourier representation, to evaluate this one, we now have this full expression. So okay, let's try to observe what we have here. We have the original integral over the Gaussian white noise measure, that's summing or integrating over all non-zero paths. And then inside this bracket would be our Fourier representation of the Dirac delta function. So if we can do these two integrals, integral over d mu and integral over your dk, the dk arose because we represented the delta function in terms of its Fourier representation. If we can do these two integrations, then we're home. I mean, we have succeeded in our task. Now, recall that I just tried to rearrange the terms in here. So this x naught and xt I put in here because the terms outside of this integral do not have the random white noise variable. So I just look at the integration over the Gaussian white noise measure, and I put inside this red circle or red ellipse everything that depends on the white noise variable. How do we integrate over the Gaussian white noise measure? Well, luckily we had a lecture last time, and the integration over the Gaussian white noise measure, which looks like this, we recall that we defined in our previous lecture the characteristic functional. And the characteristic functional exactly looks like the object that we would like to integrate. If you let, for example, this k square root of 2d to be psi, and then this integration over d mu would look exactly like this. And this has a ready answer. Remember, the way we define the characteristic functional is such that it's equal to the exponential of this minus 1/2 integral of psi squared. So on the right hand side, you don't see the random variable omega anymore. We have integrated that out. And so you have now carried out the integration over the d mu, and all you have to do is to note down what your psi squared is. So your psi is just k square root of d 2d. So if after the integration over the d mu, you just have psi squared, and this is just your psi squared. So now we have achieved or accomplished one integration, which is the integration over the Gaussian white noise measure. Now this is straightforward. Square root of 2d k are just constant, so they get out. You can take them out of the integration over time. So this part here would just be given by k squared over 2 dt. So now let's look at the result of our probability density function in the next page. After integrating out the d mu and after integrating out this time part. So we have this type of expression. This k squared 2d was the integration over time, and we are left with only one integration, which is an integral over the dk, and that dk, of course, is due to the fact that we expressed the delta function in terms of its Fourier representation. And fortunately, this is an easy integration because it's the well-known Gaussian integral. If you look at this exponential of k squared integrated over dk, there is a ready equation in the table of integrals for that, k squared dk. And so you just have to look for the coefficient of k and coefficient of k squared. That would be your q and your p squared. And by identification, the answer should look like this. And so your probability density function using the Gaussian integral would come out to be like this. You can sit down and do it with paper and pen, and it's a quick calculation with this with the help from the table of integrals. So now we have succeeded in obtaining a closed form of the probability density function using the tools of white noise analysis. And this is our prototype for the other probability density function that we will be calculating later on in this lecture series. And note that the probability density function that we obtained satisfies the diffusion equation that we are familiar with, and this diffusion equation, or the Brownian motion, is also often referred to as the Wiener process. So that's it for this lecture. We have now obtained our first probability density function in closed form for the simplest prototype, which is Brownian motion. So thank you for listening.